For example, that'll get us.
Okay, whatever you're feeling. Good to go.
Okay, so we reached this last time. We were calculating the potential at point P due to this charged rod of charge density lambda, linear charge density lambda. We'd done a trig substitution. In fact, we did two trig substitutions, and we came up with this expression. I'm going to use this triangle. I need to get back to x's so I can actually put my limits for the integral in. I know that I can write secant theta as r over a. I can write tan theta as L over a, x over a, I should say. So I can write my answer as lambda over 4 pi epsilon naught. That would be the log, and that is x over a plus a squared plus x squared over a, evaluated between 0 and L, which gives me lambda over 4 pi epsilon naught times the log of L plus square root L squared plus a squared minus the log of a. So it's a bit of a mess, but through doing that, the trig substitution, we're able to get the integral solved, and that gives us the value of the electric potential at point P for this configuration. So you see these problems can get fairly interesting in terms of going back and using your integral techniques. I'd like to do one more that does that. In fact, we probably will reach the same integral, but it's a nice problem to do anyway, even if we do get the same integral. Suppose I have, here's my charged disk again, charge Q. Let's give it a length h, the radius r. And let's say that I want to find the electric potential at a point out here. And we'll call that distance d. So it's a point d away from, along the axis of the cylinder, I want to find the electric potential. Again, what I can do is break my cylinder into a series of charged rings. Now, we already know the value of the electric potential along the axial point for a charged ring. And we can write that as V is Q over 4 pi epsilon naught square root x squared plus, let's call this radius A. Well, it doesn't matter, we're going to change it anyway. We'll call it R, fine. X squared plus R squared. So let's say so this is for one ring. Let's rename our variables. So let's say that the charge of one ring now is Q prime. That means the potential for one ring would be 4 pi epsilon naught square root x squared plus r squared for that one ring. I know that I can write my charge density, sigma, as a charge, total charge, per unit area. Area of a cylinder is 2 pi times the radius times the length h. Capital R for the whole cylinder. So I can write the charge of one ring then. One ring I can write Q prime is equal to the charge times 2 pi little r h, 2 pi little r times dx, the thickness of that ring. Or I can put it all together and write it as Q times 2 pi r dx divided by 2 pi r h. And that I can write as Q dx over h. So what I'm going to do then is I'm going to write V for one ring looks like Q prime over 4 pi epsilon naught square root x squared plus r squared. But now what I want to do, I'm going to write that as Q dx over 4 pi epsilon naught x squared plus r squared, and integrate over the length of the ring, d to d plus h. I can pull the q out of the integral, 4 pi epsilon naught out of the integral, and I'm integrating dx over x squared plus r squared, where x goes from d to d plus h. Once again, I make the substitution for tan. I let x equal r tan theta. Dx is r secant squared theta d theta. When I do that, I end up with V is equal to 1 over 4 pi epsilon naught secant theta, integral of secant theta, d theta. I have to do my secant plus tangent trick again. When I do that, I'll let you fill in the steps. For practice, I get Q over 4 pi epsilon naught h times the log of x plus square root x squared plus r squared, evaluated between d and d plus h. So this is going to be my potential at an axial point from a series of rings to make a complete cylinder. So that's V at this point P. It's kind of a nice, challenging problem to calculate a potential due to a continuous system of charges. That's all we're going to do today. We will pick up next time with capacitance, and that will be the last unit that we need to cover in electrostatics before we move on to electric currents and electric circuits. Thank you.